welcome everybody. So this week will be about query processing and query optimization. So some of you should have seen that in the undergrad lecture. So who of you has never had a lecture or any exposure to query processing and optimization? Just be honest for me, just to know. You okay? Just one. So here and there I will be repeating stuff, but if in doubt, I recommend the videos I did for the undergrad lecture. There are 2 lectures, so 2 90-minute slots of query optimization. I will not repeat all of it, so I recommend you watch these videos. Then it makes more sense what I'm explaining today. Okay, but we start first with processing and then we go into optimization. So when you look at relational algebra, and of course that's one of the fundamental things in databases, already designed in the end of the 60s, beginning of the 70s. So we had these fundamental operators in the undergrad lecture. Yeah? We can express a query on the relational model using relational algebra by just using these operators. And the idea of an operator is that you have 1 or 2 input relations and an operator produces an output relation. So like that you can phrase, for instance, a filter condition and say, this is my sigma filter operation, the input is a relation, and the output is a filtered relation. Yeah? So you can attach any predicate to the selection operator, and it gives you the tuples qualifying under the given selection. So we talked about that at length in the undergrad lecture. And based on these base operators, basically you can compose complex query plans. You notice here that there's no join symbol here. The join can be expressed, of course, by a cross product followed by a selection. So all these operators you see in these relational algebra plans are syntactic sugar in a way because they can be expressed using these base operators on top. But that's all explained in the undergrad lecture as well. So now the question is, how do we implement this stuff? So when you look at algorithms to implement that, you will see that there are certain types of classes, and all of these operators are somehow related to techniques we talk about in this lecture. So for instance, selection. A selection operator, well, if you want to select something, you can either read the entire input relation, or you have ideally an index that can be exploited because the condition is on the key used for the index. If you build an index on attribute A, and you want to have all tuples where A equals 42, well, then you can exploit the index, obviously. That's called an index access. The other option is to scan all tuples from a given relation and filter out the ones that qualify. But what I'm trying to say is this indexing is highly related to the selection operator. That's something we will revisit later on when looking at bigger plans, what to do with such a selection. If you have a selection operator in your plan, what to do with that. Then we talked last Friday, I think it was, about column layouts, column versus row layout, data layouts. Well, the projection operator is somehow related to that. The projection operator projects the wider schema into a schema that only contains a subset of the attributes. So if you project to a single attribute, that's similar to a column layout in a way. So that's related somehow to that. And then there are all these other operators. There's union, the minus, Cartesian product, which also then leads to join algorithms. All these operators, I will ignore rename for the moment, don't need it here, but these operators, also marked in yellow here, basically can be implemented using the same algorithms. It's the same algorithms with minor modifications. Those are set-based algorithms that have very similar ideas. And once you understand how to implement, for instance, a join algorithm, you will also understand how to do a set difference, how to do an intersection, how to do an outer join, and stuff like that. That's really minor modifications of these algorithms. So the message here is really for all these algorithms, it's a relatively small set of techniques that you need to know about. There's always another more fancy algorithm you can use, but for the 80–90% case, it's always the same algorithms. So let's look at join algorithms. So the typical application for join algorithm is, of course, you have a join on. You know, in SQL, you should know there are many ways to write a join. So you can either write your join predicate in the where clause, or you can use this join on syntax, which is basically just syntactic sugar. For union operations, you have these intersect and except statements, which vary across different database products. And you also have group by and aggregation. Even the algorithms for grouping and aggregation are very similar to join algorithms, which is due to, long story short, due to the way how these operations were defined in the 70s, which can be debated. But basically, grouping and joins are super related. We will get there when I explain join algorithms, then you will see there's something in between joining and grouping, actually. It's called co-grouping. Today, this is called factorization. Just for you to know, yes, so you have two different operations in the database system, a join operation and a group by operation, but in spirit, it's actually the very same operation. It's the very same operation. However, SQL doesn't allow you to specify that directly. So this is a historic decision that was taken. Yeah, the same is for subqueries. Yeah, if you write it, we had that also in the undergrad lectures. You can nest SQL queries. You can write another SQL query in the from clause or in a select clause. And then eventually you have to understand how to execute such a SQL statement. These subqueries can often be rewritten to a join. So you write down a subquery, but the optimizer decides to, oh, I don't care, I rewrite that to a join. Yeah, then the subquery is gone. There are many techniques for optimizing subqueries. Okay, so the good news is there's only 4 principal classes of join algorithms. And again, if you understand join algorithms, you understand grouping, you understand intersection, you understand basically all the important techniques. Nested loop, index nested loop, sort merge, and partitioning or partitioning using hashing. So we look at that in detail. So this is a super fancy algorithm called nested loop join. So what does a nested loop join do? It creates 2 loops. So here you have what you want to join is all tuples from R, join with the tuples from S under a certain join predicate. So here's a join predicate is R.x equals S.x. That is a join predicate here for whatever reason. And how do you do that? Well, you do a loop over the elements of capital R of relation R. For each small r and this big R, you have a nested loop. It's called for each S in S. Oops. So for each S in S, another second loop. And then you check whether for this particular combination of small r and small s, this combination qualifies under this join predicate. So each possible combination of R and S is checked, and only if that is the case, you output a join result. That's called nested loop algorithm. Algorithm is a big word for this thing. It's a nested loop. 2 nested loops. What can go wrong? So what can we say about this algorithm? What should come to your mind immediately? How is it related to relational algebra? What's the counterpart in relational algebra? Yeah? Yes, exactly, the cross product. The cross product does exactly that. What's done here in these loops, that's the cross product. And what I'm adding here in the nested loop join algorithm is to do the relational algebra operator. Selection. That's my selection operator. So what this algorithm is doing is basically literally implementing this expression, saying, okay, for R and S, I really compute the cross product, which is a squarish number of results, And then for each tuple produced here, I check whether that tuple qualifies under the given condition. The slight difference here is that I don't really create a combined tuple here. Yeah, so I don't do that here. You could also create one big tuple first and then define your joint predicates to operate on this, this bigger tuple, R concatenate S. Yeah? I'm not doing that. I have it as separate parameters, but that's a detail. Yeah? But the core idea is the same as here. Okay? So that's basically literally implementing the cross product from relational algebra plus a selection operator afterwards. So how efficient is this?
Very efficient. N over to n squared.
N?
N squared.
N square, yeah? Squarish complexity. So the number of comparisons is number of tuples in R times number of tuples in S. Yeah? Squarish complexity. Yeah, if you simplify that, the number of tuples in R is equal to the number of tuples in S. Yeah, then that leads to, you have, define N, let's do it capital N. Yeah, then that leads to N square comparisons, yeah, because each tuple from R is compared with each tuple from S. Yeah, so it's a very inefficient algorithm. Still, it can be used for small data sets. With today's hardware, yeah, you could use it, yeah, but of course you may fall off the cliff, yeah, because once you increase the data sets, it's kind of a denial of service attack on a database system. Yeah. If you use this blindly, yeah, that may ruin the entire performance of your system. So you have to be careful. You cut the scenarios where you use that. Okay. What is another thing? We can go back to that once we discuss the other algorithms, but one that's very important about this algorithm. One is I don't restrict the predicate, any predicate. I don't care. Whatever predicate, this is going to work. Yeah? So you call the predicate directly in the code, or here in the selection operator, you write down the predicate here, it's going to work, it's going to fly, and that is fantastic. Yeah? And this is not true for the other algorithms I will be showing in a moment. And in terms of software engineering, of course, that's the first thing you implement. Yeah? To get the reference set, for instance, for end-to-end testing, yeah, you implement a new, same as with indexing again. In indexing, we had this end-to-end test where if you want to check whether your index is correct, you do a full scan, filter out the tuples from the base relation, compare the result set with what the index returns. That's your end-to-end test. Same here for join algorithms. End-to-end test is cross product followed by filter, compare the result set with your join algorithm, and then you see whether that's the same thing. Yeah, so that's very important in software engineering terms. Okay, index nested loop join. So that's a variant where I'm fortunate enough to have an index. This is brilliant. Okay, it's the right glasses, but still. Okay, so this is, here you see there's only one loop. And what I'm assuming here is that I have an index on R. So I have an index available on R, and that index was built on the join attribute. So I have an index where the key is r.x. That's fantastic, yeah? Because now I can do the following. I get rid of this loop here. This for each R and R. I don't need that anymore. I only need the yellow loop here. So I basically probe the index for each element in S. Yeah? Rather than looping over the elements of R, I check for each element in S whether it has an entry. So here, that is the index on R, and I send a query here for each of the small s's with regards to the x attribute. Yeah? Recall that the join condition is r.x equals s.x. So with that, I can directly look up for any tuple S whether it has a counterpart in the R relation. I directly get the results. Yeah? The condition here is equality, which means I define joining tuples by the r.x attribute is the same as the s.x attribute. If r.x is 42, s.x must be 42. So I'm just exploiting the index to directly look up those values here. If that returns the result that's being checked here, so if that result set being returned is not empty, I output the tuple s. I put it in square brackets to convert it into a set, cross product the query result set returned there. Yeah, that's what I'm adding to the output. So for each tuple being returned by the index, it may be multiple tuples, I return the tuple of s cross product the tuples returned. So the number of tuples here is equivalent to the size of the entire output set, because I'm only adding one tuple from s. Yeah? Is that clear, more or less? Yeah?
Could the algorithm be optimized if we sort the table S already on the join attribute, and then if we have basically multiple the same values of as x, for example, take this group, then
Yes.
query the index once,
Yes.
one value?
Yes. Yeah, that's another reason actually why grouping and joining is very similar. So if you have, if your S relation contains duplicates with regard to s.x, then what happens is you will be doing the same lookup to the index on R multiple times. So if you have 42 appearing multiple times here, blackboard. So we have this relation S, we have an X attribute, and whatever foo attribute. Yeah, that's what you were saying. So basically, they may appear anywhere. Yeah, so it doesn't have to be adjacent. Yeah, I'm not talking about any order here. I'm not assuming any order. Again, my relations, underlying relations are sets, no order implied, and so forth and so forth. So here's 7, eventually is 42. Yeah, so it would be kind of a waste to ignore the fact that there could be duplicates, because I will be doing the same lookup multiple times. It would be better if I could group those entries from X with the entries from the other relation. And that exactly leads to an algorithm that's called co-grouping. We will look at that later on. And there you will see that grouping and joining are actually the same thing. That's just legacy in relational algebra and SQL. Huh? But very well observed. I have separate slides on that. Yeah? We'll go there for the moment. For the moment, I assume I ignore that optimization and many other optimizations you could do here. In particular, when you look at the underlying I/O, you can also play tricks and add more loops to that. But that's a different story, maybe for the assignment sheet. Yeah, so far so clear? Yeah, so this blindly, that's what you're doing here, blindly checking these comparisons. I just check directly here using the index whether the element of S has a counterpart, has a join made or multiple of those in relation R. And if that is the case, I produce a join result. That's the idea of the algorithm. Okay, and that leads to something that's called simple hash join. And the only difference to what I explained before is the following. If you look here, in this index nested loop join, I'm in the comfortable situation that I already have an index available. So the index is already there. I don't have to build the index. It was already built for me before. Yeah? So the query comes in, and oh yeah, there's already an index on R. I don't have to do anything. I can directly exploit that. And that's different here. In a simple hash join, you can use any index, but typically use a hash table. The idea is, okay, you want to run this join algorithm. You don't have an index, and then you create an index on the fly. And the index will be a hash table. So the first thing you do is you create a hash table. And programmatically, what happens here is, that is your hash join algorithm. Hash join algorithm. Well, I call it simple hash join again here, right? Simple hash join. Simple hash join. Yeah. And you write this as operators. You have R, you have S. So what I'm doing here in that code line, index this build hash table, code line that's marked there, I create a hash table here in the algorithm. That's my hash table. And that's the first thing I do. You often see these visualizations in database literature. So I consume all of the tuples from R. I read all tuples from R. That's what the loop is doing inside the build hash table operation, and insert those tuples from R into my hash table. Once this is exhausted, once I considered all tuples from R, the next phase of the algorithm starts. This is also called, so building this. Whoops, any questions? This is called the build phase. Build phase. Yeah, in the sense that you build the hash table, and now comes the second phase, that is, for each tuple from S, you probe the tuples from S against the hash table. Yeah, it's something like this. Yeah, so this is called the probe phase. Probe phase. Yeah, those are fixed terms in that world. A build phase, probe phase. So this is the probe phase you're seeing. Except this build hash table that's basically running the build phase, but then everything underneath, like here, is a probe phase. That is a probe phase. Probe phase. So all the tuples from S are probed against the index you just built in this line here. Yeah? And then it's the same logic as before on the other algorithms. Aha, you find something in the hash table, then that means there is equality, and then you can return a result set. Okay? Any observations here that are weird? Code review. Yeah, I assign you as a reviewer in GitLab. What are you saying about that one? What's weird? Seeing this code maybe written in Python, and then you should hit me hard with comments. Yeah.
So we're building the same thing we had in the index. So we have.
You mean here?
On Rx, we can use that as we did here.
No, let's assume there's no index in the catalog. There's no suitable index available. Yeah, I really have to build it while or before running the probe phase. Yeah? I really have to build the index for it. So it's bulk loading an index here. And typically it's thrown away immediately after I execute the thing. But what's weird in terms of code, if you see code like that? Yeah, let's ship that to production. Sounds like a great idea, Jens. You're the professor. You should know how that works, right? What is special about this algorithm in particular when compared to nested loop? Yeah. And even here, I would probably, not sure, maybe that's the right way of doing that. Maybe even here I would add an assert statement here, checking the sizes of R and S, and if the sizes are above a predefined threshold, I would say, are you sure about that? The inputs are really big. You want to go down that rabbit hole and execute this, even though that will take a long time. At least a warning, right? But there's something, ignoring performance, there's something functional that's different. Yeah? Yes, exactly. We're restricted to equality predicates here. Yeah, so I write down this stuff here. Yeah, equality. And then I pass it as a parameter because probably that's a generic interface somewhere. But do I use this stuff? No, at no point in the algorithm I'm exploiting the join predicate. I'm making a hard assumption here that, yeah, you pass me a join predicate, but do I care? I don't. Same holds here. So I don't really refer to the join predicate being passed or the attributes mentioned in the join predicate. It's a redundant way of specifying that. So the least thing you should do in the code is to check whether the join predicate is an equality join predicate. And the second is to get the attributes of the equality condition from the join predicate and not hard-coded them as on this slide. Yeah, that's a very important thing to do. That's something you should write in the code review. Yeah, right. So the simple hash join is restricted to equality. There are variants where you can do things that are not strictly equality. Then you need hoops and different indexes. For instance, if you have an index supporting range queries like B-trees, you can actually express certain other join conditions, but that's a different story. So this can be extended. Okay, right. Build the hash table. Also, that's yeah. So, and that's basically the difference to this index nested loop join. Again, I'm just the messenger. Yeah? So the algorithms were named like that. It says index nested loop join and simple hash join. Again, it's actually the same algorithm. The only difference is when do you build the index? Yeah, index nested loop join is typically assumed to, the index is already there before I execute the join. Simple hash join is more like, oh no, there's no index, I create a hash table, which is an index. Yeah? But in spirit, it's the same thing. You have an index either being built before or on the fly, and then you probe the other relation against the index. That's it. Yeah? Those are those algorithms. Okay, right. Yeah, with that we enter sort merge join and co-grouping. And I have two relations, I want to join them. Yeah, so this is basically the use case we had last time. So we had customers, and I had the city, and I replaced the city by dictionary compression. Yeah, that's exactly what we did last time. And I want to join customers with the cities dictionary again. And I will do that using a sort-based algorithm that's called sort merge join. And to execute that, the first thing I do is I sort on city ID. So customers has to be sorted on city ID, and cities dictionary has to be sorted on city ID. That's what you see here. Now it's sorted. Whether it's ascending or descending doesn't matter. It just has to be the same order, sort order in both of the relations. Now I keep two pointers at all times that point initially to the first entry. So this is 0 in both entry, city ID 0 here and city ID 0 there. If both pointers point to the same ID, to entries that are similar, you produce an output result. That's happening here. Yeah? Already with the first tuple, both point to 0. I produce an output result, and that's this one. Yeah? So this is a joint result. I'm producing Frank Min Street living in New York, and also keep the city ID here. You probably know that from the joint semantics in SQL. Typically returns both joint keys redundantly, and there are all kinds of things may happen. So I'm only returning this ID column once here in the example. Now we returned this tuple. Now we move the pointer forward that points to the currently smallest element, which is not clear here. You could move the left pointer or the right pointer. They're both pointing to the same element. If in doubt, you have to move that pointer always that points to that column that has duplicates. And otherwise, you would be missing results. So here I'm not allowed to move the yellow pointer. I have to move this pointer on the left. That happens here. Again, now this pointer points to 0, that points to 0. I produce another join result that goes here. Again, I have to move the pointer forward that points to the smallest element. If in doubt, tiebreaker, pointer on the left. That's what I'm doing here. Voids point to the same element, another element is being produced. Move the pointer forward, the values are not equal, no join result is produced. Again, move the pointer forward, pointing to the smallest element, which happens to be the yellow pointer now. Now I'm here. Again, both elements are equal, produce a join result. Move the pointer forward, that's the smaller, this points to the smallest tiebreaker, both point to 1, aha, so I move this one forward, and so forth, and so forth. So basically I concurrently, not concurrently in the sense of multi-threaded, but I step through these two columns, yeah, always moving the right pointer forward, and whenever I have both pointers pointing to the same ID, I produce a join result. That's the idea of a sort merge join, and so forth, and so forth. Right. Maybe let's switch here. It's a very long example. Back to my iPad. So that's the algorithm. So what you need to have is the sort order. You sort R on Rx, sort S on S dot X. If it's already sorted, similar to the situation we just had with the index is already there. Here, it could be a situation that the sort order is already there. Well, how could it be that the sort order is already there? It's already available. So you're accessing all the tuples from R or S, and the database catalog tells you, yeah, it's already sorted. Why do you want to sort it again? It's already sorted. How could that happen? Yeah?
When there is a B-tree index?
Yes, exactly. B-tree index, for instance, if you have a B-tree on R and the key is X, then it's already sorted. That's what we learned when talking about B-trees. Yeah? That's one situation. Other situation. How could that happen that it's already sorted on one of the inputs? Assume you do a sort merge join here. Yeah, and assume it's whatever, R dot X equals S dot X. And assume this join is S dot X equals T dot X. You do a sort merge join here, you sort on that X attribute, then that means the output is sorted on X as well. Then here, you already have a sorted input with regards to the same join attribute. So the only thing that needs to be done is sort on T dot X. Yeah? So there are effects here where you see, aha, you can exploit something that happened before. You exploit something that happened before could mean, I have a B tree on that anyway, so it's sorted. Fine, that happened before. Yeah, and the same may happen here. It happened before that the stuff was sorted anyway. Maybe it was also sorted due to some other operation. Maybe it was sorted due to the user specifying an order by or whatnot. I don't know. Yeah? But if there's a sortedness already, you can exploit that directly in the algorithm. Yeah? Yeah, and then that's what I just explained. You basically have these pointers here that are initialized to point to the first element of these streams, and then you step through these inputs. We have to be careful about is these when the keys are equal. That's what I just mentioned. So here's again this example. Présentation. Here. Yeah, so we have typical foreign key situations. We have a lot of duplicates here, and we have a key column here. Yeah, and then I said, okay, then you move the pointer on the left. That's what you do. And yeah, the question then is what happens in this kind of situation? Assume for whatever reason you do a join like that. And actually, this should never happen in a well-designed schema. It's hard to justify, not a long foreign key. If you know, this basically is an N to M relationship. Yeah? The relationship we had before is 1 to N. Yeah? One element here can be associated with N elements here, a classical 1 to N relationship. If you have an N to M relationship, an N-T-relationship modeling, you translate it into 1 to N and N to 1, into 2 of these relationships. This means this stuff here actually is kind of a different case. It's not the standard join along the foreign keys case. Yeah? But still, let's assume it happens. And there are cases for that in RDF data management and whatnot, where you actually do these kind of things. Yeah? But what do you do with the sort merge join algorithm here? Yeah? Yeah.
Then we move the other pointer.
Right, yeah, so basically when you enter the 1 here, so what you're suggesting is, maybe I'll scribble again on my iPad a bit. So when you're here, yes, so you keep a pointer identifying where the start is within the current group, yeah, and then you still keep on looping, on the wrong slide, here. Yeah? So you would have, I mean, you have to go back at some point, yeah, because now within this here, you have to combine all of these tuples here with all of the tuples there, and then you have to get back to the start of this one group and so forth. That's basically what you're saying. Yeah? Huh?
Also, in parallel, basically compute for both tables, you compute the groups with the equal value of city ID.
Mm-hmm. Right, exactly. And that is what's called a co-group join. That's visualized here, because that's happening conceptually here. Yeah. So here I'm joining the cells of those values that have the same ID. Here see, this is a 1 and that is a 1. And the combination of those subsets is called a co-group. Co-group meaning, so one co-group consists, for instance, of all tuples that have the key 1, followed by the tuples from relation customers. Yeah? So the customer subset, I write it as customer 1. Yeah, that's a set of tuples. That's those 2 tuples. And then the set of tuples from the cities dictionary, let's call it CD1, that have that value, that's those 3 tuples. The entire thing, you can write it as a tuple, is called a co-group. You know grouping, so far you've seen grouping only with regards to one relation. That's what you do when you do group by. You can only do a group by on one relation in SQL and relational algebra. There's one input table. Yeah? If you want to group on multiple input tables, you first have to join them or build a cross product or whatnot. Yeah? But the input to the grouping operation is always a single table. Here, we group on multiple relations, in this case 2, at the same time using the same condition, saying I want to have those subsets, those partitions where the key is equal to 1. And you do that, of course, for all occurring keys. So there's another co-group, for instance, with 5. Yeah? Again, this is cust5, cd5. Cust 5 being, okay, those 2 tuples, obviously, where city ID is 5. And here it's those 2 tuples. Yeah? And there could even be, you could even then go to something like whatever, 0, cust 0. That's cust 0 is these 3 tuples, and here's nothing, so that's an empty set kind of situation. Yeah, that's called co-grouping, and that is actually what the sort merge join algorithm emulates in a way. The sort merge join algorithm folds 2 algorithmic levels into the same code. And what you were just saying is actually the better solution in the sense, so once I have these co-groups now, what do I have to do with these co-groups? You said it already, but maybe someone else. Yeah, I have an algorithm that does exactly that, that that builds those co-groups. But that's not what I send to the output, right? Because the output is flat tuples in relational algebra and SQL. So I can't, actually you could put the co-groups with a statement called array to the output. Longer story. But yeah, but if you want to have the flat output, the stuff we produce with nested loops or the standard sort merge join algorithm I explained before, what do you have to do? After the guy after you, yeah. Cross product, but like how? How exactly? What do you mean by cross product?
So is there a tuple in the second element with each element in the third element in cluster?
Within a co-group.
Yeah.
Yeah, so within each co-group, you compute the cross product of this set and that set. Why doesn't this work now? And that set, yeah, and so forth. And that produces a certain number of tuples. So for instance, for the 1, we have 2 tuples here and 3 tuples here, 2 times 3. That will produce a 2 times 3 tuples, 6 tuples in the cross product. That would have been produced by nested loop or sort merge join if adjusted in the first place. Yeah? So it's a 2-level process here. Yeah? And the same holds for this one. He would do the cross product of those tuples with the cross product here, so 4 tuples would be produced if you do a cross product of cust5 versus cd5. Yeah? And that's a much better way of modeling if you do it like that. Yeah? If you understand this algorithm, you can do crazy things. You can also adjust that to distributed joins and joins on NUMA and data centers and whatnot. It will always lead to this algorithm, slightly tweaked. You know? Okay, but that tells you that co-grouping and joins are actually highly related. So another term that's used these days is basically that's called factorized databases. Factorized meaning factorized databases, meaning that here you have a representation where you did not build the join tuples, the concatenated tuples, but you keep the individual tuples in their representation. Yeah? If you think about, we talked about that when talking about result DB. Yeah? Very similar idea. Okay, and that leads to an algorithm that's what I'm calling the generalized co-group join. Yeah, so these groups are called co-groups. I explained it already. Here I color-coded them again. So green doesn't have a counterpart. Blue have a counterpart, so they are connected actually. Those are the groups. That's another visual representation of that. And you can do that without sorting as well. So this building or identifying co-groups, performing a co-grouping operation is not restricted to using sorting. Yeah, here's a situation where we did not sort. Still the colors belong to each other. So all the 9s here, yeah, build one all these 9s across both relations build one co-group. Yeah, and that leads to a generalized co-group join. So generalized co-grouped join. Oh, come on. So the idea is you partition R into subsets. That's what happens here. Then you partition S into subsets. That's the co-partitioning. This only makes sense if you somehow use the same partitioning function or partitioning function that can be related somehow. Otherwise, you cannot play the cross product trick we just learned about in this equality join. And then for each group ID or for each co-group, you do something. Yeah? You get you have the left input, you have the right input. That's basically what I denoted here in this here where I scribbled the co-groups. That's the left input here, that's the right input, yeah? And that's my co-group here, one of these tuples. That's what we're looking at in this algorithm. Then you can check whether one of those is empty. Then it doesn't make any sense. You don't have to continue. But then basically, you're not restricted to creating, to executing a cross product here. You can actually create any other join. Yeah? So in the example we saw in the first part today, we do the cross product. because we build co-groups based on identity. We know within the co-group, in the left set, all the IDs are 1, and in the right set, all the IDs are 1. They're all the same. But now I'm doing something more generic here. I'm saying, okay, there is a group, and that was built in a certain way, and now rather than doing a cross product, I do a whatever join. And to make that more concrete, let's assume we're in a scenario where you have two relations, R and the relation S. And let's assume this doesn't fit into main memory. Yeah? So the memory could accommodate R, maybe twice as R. So let's just have a different color here. No, I don't have it. So assume the memory is something like that. So you could load R into memory, but you can't load S. Yeah, so how would you join? How would you perform a join in this situation? So this is main memory. So somewhat maybe 10% bigger than R, but you can't load R and S at the same time into main memory. So how would you execute the join? So it's similar, we talked about this sort merge join, external sorting. So this is an external memory situation again. External join situation. So the join the inputs cannot be loaded fully into main memory. How do I execute the join? It's not co-grouped. So there's no sort order whatsoever. I have the same condition here, r.x equals s.x. And I have no co-grouping whatsoever of relation R and no co-grouping whatsoever on relation S. So what could I do in that situation? Yeah?
I think the native way would be to say my memory has a certain size, and now I split both relations into chunks of the memory size divided by 2, so that I fill up the memory size with both chunks.
Mm-hmm.
And then I could basically fix one chunk for the one relation, then go through all chunks of the other relation, and compute all join results or tuples that should be part of it.
Yeah, how do you compute chunks? How would you compute the chunks?
Basically, by just saying a certain amount of main memory, and then saying
Okay.
I take so many tuples from R, then
Yes. Okay, so basically let's assume you compute whatever. Something like that. Yeah? So you have like R and S, and now basically you partition R into 3 chunks. Let's say let's call it R1, R2, and R3, and S1, S2, and S3. So you chunk that. You just have to make sure that any pair of these chunks, so R1 and S1, R1, S2, R1, and S3, and so forth, fit into main memory at all times. So now you're basically computing a cross product across those chunks, right? Sounds like a neural network. I'm also doing AI now, right? Okay, right. But this is still square complexity with regards to the chunks you're comparing. Yeah, and also with regards to the tuples. And that's not what I'm aiming at. For one may answer, and then I will reveal why that is a trick question. Okay?
External sort S and just create a group on fly when we are reading S.
Come again?
We can external sort S and just create the co-groups on the fly.
Yeah, would be so external sort S and to create groups after sorting. Yeah. And for R, you do it in main memory. Yeah, that would be one way of doing that. That's fair. But you're already all on the wrong track. Because I said, I will get there. Yeah? And that it leads in the right direction. However, in this situation, if I say, okay, R fits into main memory, but S not. Or even S fits into main memory, R fits into main memory, but not both of them fit into main memory. That doesn't work. So if one of the relations fits into main memory, I can use simple hash join because I can build a hash table here on R in this situation, and I don't have to keep all of S in memory at the same time. So in a pipelining fashion, we will get to there with many slides on that, but basically there's, even if you look at the algorithm, you see, if we go back, where's my simple hash join? Here. Yeah, the simple hash join. So what do? I just loop over the tuples from S, and once I queried the hash table, I don't care about that specific tuple anymore. So at all times, the only constraint I'm having is one tuple from S at all times. There's no built-in need to keep the entire relation S in main memory at all times. I didn't say that at any point. If you implement it like that, okay, then you're screwed, but you don't have to. Yeah? So it's one tuple at a time. So the memory requirement here is only one relation must fit. And that's also the reason that you typically in simple hash join, you build the hash table on the smaller relation. And you check which one is smaller. Okay, that's my relation to build the hash table on. If S were smaller, you would probe everything from R against S and so forth. So in a situation where one of the relations fits into main memory, there's no need to play more advanced tricks. Yeah? So let's assume main memory is smaller. Yeah, so they don't fit into main memory, and none of them fits individually into main memory. Then we do something that goes in the direction of what you were saying. But there's one important thing you have to be careful about. Because when you look at how I explained this, yeah, I built co-groups on equality. Yeah, on the so I created in a way that for each distinct ID in those columns, I create a co-group. Yeah. So. Yes. Okay. Sorry. It's flipping back and forth. Okay. So for each distinct ID, I create a co-group here. Yeah. Now I'm solving a slightly different problem. Yeah, because the problem, or what I'm trying to do now is, so when we go back to this situation, I want to end up in a situation, maybe I scribble it down again. So I have these three partitions here from R, and these partitions from S, S1, S2, S3. This is what R1, R2, and R3. And I don't want to combine them in a nested loop fashion. I want to create co-groups like this. Yeah? So such that it's guaranteed that I only have to join this chunk from R with that chunk of S, that chunk of R with that of S, that and that, plus the condition that for all of these co-groups, at least one of the subsets fits into main memory, because then I can execute simple hash join. Yeah? It could be that obviously these R partitions fit into main memory, or the S partition, but it doesn't matter. You can always swap. Yeah? As long as for each of these three co-groups, one of these sets fits into main memory, I can run simple hash join, for instance. Yeah? And you see it here on where's my iPad? Not here. That's basically what this line is about. Yeah, whatever join. Yeah, whatever join. So we want to go to a world where I instantiate simple hash join 3 times. Yeah? So there will be one simple hash join here, one simple hash join here, one simple hash join here. And the invariant in partitioning we did before was strict equality. Yeah? So this was all 1, 1, 2, 2, 3, 3, and there were zillions and gazillions of these co-groups. Yeah? If I want to do something like that, a join wouldn't make sense. I can directly do the cross product. Yeah? Now I want to do a more coarse granular partitioning to chunk it into these 3 partitions to have these cogroups to be able to load the stuff and execute simple hash joins. So how could I do that? How could I co-partition my data? Yeah, partition. And now I want to divide the input of R into 3 relations. 1, 2, 3 I said, right? Okay, not 0. R1, nah, I need 0. I would prefer 0 here. 1, 2. Yeah. And then I would do the same for S, of course. S, S0, S1, and S2. Maybe I adjust my indices here on the right side. Yeah, so this would be numbered from 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay? So how do I do that? How do I partition such that I end up with these 3 horizontal partitions of R, and these 3 horizontal partitions of S, such that here's my cogroup on S0, S1, S2, and so forth. How could I do that? Right? Why does that work? So whatever, for X, you do the same for S, of course, yeah? For S, you, same attribute, then you do S dot X modulo 3. It's a partition on R, it's a partition on S dot X. Why does that work? So here's everybody where that for R dot X modulo 3 is 0. So it can be perfectly divided. Here where the modulo operation is 1, here where the modulo operation is 2. Same here for S. What does that imply? Yeah.
In that case, if you had 0 and 9, they would both go to R0.
If you had 0,
Like in the table representation, you had 0 in CD80 and also 9. And with mod 3, they both go.
Right, good example. Yeah. So 0 would go to 0, 3 would go to 0, 9 would go to 0. Yeah? That's one part of the explanation. That's how you partition R. So you partition S, same rules apply. So that means if the keys are equal, they end up in the same cogroup. If they're different, they may be ending up in different cogroups, but they don't have to, because, here's a perfect example. Of course, the 3 also goes to partition 0. The right ID, 1125. Yeah, of course, 3 also goes to 0, and that will be eliminated in the join. And this kind of partitioning is exactly the reason why you wouldn't be allowed to do a cross product here. that would produce wrong results. But the join you initialize later on these co-partitions, the simple hash join, will remove all of that. Yeah? The purpose of the join is to just be able to, the purpose of the co-grouping operation is here just to reduce the input data set such that something like this actually works. Yeah? You don't have to go down all the way to do the full-blown co-grouping, with regards to identity within the co-group. But if you partition like that, and you could also, I mean, for instance, so the number you use here, of course, determines the number of partitions, and that should be chosen based on what is the available memory, how big are my input relations, is the ID column skewed somehow, yeah? So with the hope that this works out in a way that you can execute the join. You might have to repartition even. You partition it once and have to repartition it a second time. May happen. But once you partition your data like that, then the magic happens, because now it's guaranteed that whatever sits in R0 must never join with anything in S1. Same here, R1, there cannot be a join result with S2, because the model operation is different, and so forth and so forth. So I'm getting rid of all of these, for each relation I get rid of all of the edges except one, to the same partitioning result. Yeah? And like that I kill this nested loops partitioning property I would have to do if I don't do semantic partitioning. So what you suggested here, this stuff, is actually called chunking. Yeah, you divide R, ignoring the semantics, ignoring the data values, into chunks, such that you can do nested loops on the chunks. Yeah, what I'm doing here is semantic-based partitioning, and the semantic-based partitioning can be exploited here to do co-grouping very efficiently. Yeah, so once you did that, and this entails you load R, partition it, write out the partitions, you load S, partition it, write out the partitions of S. But then, in the second phase, you can run a join partition by partition. Yeah? And all these results are then sent to the output and produce a final join result. Okay? Yeah, that's generalized co-grouping. And it also works in the distributed case. Assume you have two machines. Server 1, server 2, so server 1, server 2, and here's R, and here's S, and then you're going to compute the join on that. Well, what you could do is well, okay, you have two servers to compute the joins. You can run a partitioning function modulo 2 actually, and say, okay, all the tuples where the modulo for the partitioning function returns 0, all these tuples should be here. Yeah, so P goes to 0 goes here, P goes to 1 goes here. So basically, I mean, you have all tuples from R here already. Okay, yeah, but you have to find out, okay, which of these tuples are partitioned to 0, and the same here, which of these tuples are partitioned to 0. And then you only have to send over those tuples from S that partition to 0. Yeah? There's a subset of the tuples here, the S0 partition. Let's call it S0 and S1. Same here, R1 and R0 and R1. Yeah, then you send over this stuff here, for instance. Yeah, then you can do the join of R0 and S0 locally. You also send over this R1 here, and then maybe do R1 and S1 locally on the server 2, stuff like that. Yeah, this has a gazillion of applications. Yeah? This join can also be adapted to NUMA scenarios if you have your partitions on different NUMA regions, networks, and whatnot. It's always the same idea. It's just tweaking where to load these partitions, how to use a the partitioning function, and then what join to execute. Even here in the whatever join, it does not strictly have to be a main memory join. It could even be another external join algorithm. You could even recursively call, for instance, a generalized cogroup join, and inside use a different generalized cogroup join with a different grouping strategy, with a different partitioning function. No? Everything's possible. No? And with that, you can mimic a very famous algorithm, and database is super old. It's called Gray's hash join. It's basically doing what, it's a special case of what I explained here, Gray's hash join. And that's a play of words because what's meant is a famous researcher called Jim Gray. Yeah, and if you say Gray's, it sounds the same as that one. But that's just a footnote. Okay, here, generalized cogroup join. Right, so here's another visualization where I do that, partition one input based on the function. Then here's the same, and then you build these core groups. So join one core group, join the next core group, and so forth and so forth. So, yeah. So as promised, now you know about grouping. Now you know about nested loop join, hash join, and sort merge join, and partitioning joins in the sense of co-grouping. But let's look at the standard grouping. So standard grouping in sequent relational algebra, where there's one input relation, and you group it based on a certain condition. And the interesting thing is, again, this is like the co-grouping algorithm I just showed to you with two relations just done on one. It's the same thing. And there you see the similarity. There's no difference between co-grouping on 2, 3, 4, 5, or 1 relation. So you can do grouping based on hashing, or you can do it based on sorting. And the hashing variant is explained here. So what you do is you build a hash map that maps from the grouping key to the set of tuples that have that grouping key. Yeah? In SQL, you always write it like, whatever, select x, count star from R. Is that a valid SQL query? Of course not. Why would it be valid? I'm returning something here that is not unique in my group. Here I'm basically, the count star is just saying, okay, I return an aggregate. Yeah, and the x may be different across different groups. Yeah, the standard, you see it when you add the group by and say group by y. How could that be? Because within a group I'm building here, x doesn't have to be unique. Yeah? So it's important that whatever you write here as x, if you write something here that's not an aggregate, it must appear in the group by. There are exceptions to that when you have a functional dependency. Yeah? If you're unsure about that, check out the undergrad lecture slides. I explained it in detail. But where I'm here is now, what I'm saying is when I compute that with a hash-based algorithm, I basically just create a hash table using the grouping condition as a key of my hash table. That's all I'm doing. Yeah? And then I associate with each of those keys, that's if it's 42, I put there a set of tuples that have that key in the x attribute. That's the first thing I'm doing in grouping. I partition by this x attribute. And that's what you see in the pseudocode here. So I loop over all the elements, and then, okay, you can do that in Python, one line, of course, set default. But basically, you bulk load the hash table here. Yeah? You put this key r.x comma, a list here, or this group or set of tuples having that key. That's all you're doing. That's basically the partitioning phase of the algorithm. And then in the second phase, you do the actual aggregation. The second phase looks at the hash table. So if he were to do that in Python, that would be an items iterator, looks at all the key value entries from the hash table. And for all the entries you find, you have to pipe the group, the set of tuples having that specific key, through the aggregation function. Yeah, so for account star, yeah, assume you had two tuples that have whatever, x equals 42. I didn't write the time here, come on. I will have fun editing. So if two tuples from R have 42, for instance, in the x attribute, yeah, then this set will contain these two tuples. And now what I'm doing is I pipe this set through the aggregation function. The aggregation function tells me what to do with a set. It can be minimum, maximum, average, on attribute, and whatnot. But here I'm just counting the number of tuples in that set. Yeah, and that happens here. So in the code, I get the aggregation result based on my aggregation function. And this is count, I get the 2. Yeah? And then I output that as a result. So here I form a new tuple, which is the key and the actual aggregation result. And I hope you remember from the big data engineering lecture that for each group identified in group by, there's one tuple in the output being produced. Yeah, each group produces one tuple. Really read back the stuff if you're unsure. Yeah? Very important also for the exam. Yeah? So the group by has this weird semantics. It's 3 operators at the same time: partitioning, aggregation, projection. We're currently working on fixing that in my group. But yeah, it's 3 different operators. And that's how it works. And you see these different aspects here in the algorithm. Yeah, and sort-based, well, how is it done sort-based? Sort-based means you sort the input on the grouping key. That's very similar to what we had here in, if you go back to, where was it sorted? Here, I think that's a good example. Yeah, assume we forget about this other relation for the moment. Yeah, so we just look at this relation here. Those are the groups already, just that it's not co-grouped currently, but those are the groups I'm interested in. Yeah, and of course, these groups are adjacent to another. If 2 elements belong to the same group, 2 tuples belong to the same group, after sorting on city ID, they're adjacent. Yeah? By forcing ordering, you get this adjacency. Adjacency doesn't matter anything in the relational model, but once you swap to sequences, once you sort and have a sorted sequence, then you can do this kind of stuff. And then you know, okay, if it's the same adjacent and the same value, it's a group. Yeah? So if you step through these tuples and you see it's still the same ID, then you know you're still in the same group. Once you see, aha, now I'm in it, I see a tuple that has a different ID than the one I've seen before, you know, a new group started. And that's basically the signal telling you, aha, I have to start a new group. So all you have to do is step through the sorted sequence of tuples and do a couple of very easy checks. And you see it here. You basically keep a current group value. Yes, you start initializing that with the x value of the first tuple you're looking at. Yeah, and while you're still seeing that value, you know you're still in the same group. But once that changes, a new group starts. That's just a matter of identifying, okay, is that still the same group or the new group? If it's still the same group, okay, everything is fine. And once you are closing, once you see it's different, that's basically what this check is about, then you start a new group. But if it's the same group, and that's basically this branch here, then you append to a list, and you collect all of these tuples belonging to the same group in the list. And that's what the algorithm does, so very similar. And then afterwards, it's the same as in simple hash join. you call the aggregation function on this particular group. So for each group, you compute one output tuple. Yeah, that's sort-based grouping and aggregation. Okay, now let's combine that with what we talked about when talking about external merge sort. Let's assume we're in a scenario like this. So if we group by A from a table and then do a count star. And the naive way of doing that, if the sorting is external merge sort, is you run external merge sort and then you run the algorithm I just showed. So you keep it independent. You have your sort algorithm producing a sorted stream in any pipeline fashion. The sorted stream then goes to your grouping, your sort-based grouping algorithm. Yeah, that's a strict separation of these two algorithms. Now I'm about to merge these two things in the next slides. I'm basically pushing down the semantics of the grouping operation into the sort operation. So the late grouping, as I call it here, is done after this stream is produced. Recall that this is this final merge is actually can be done online. Also in our Python implementation, it's done like that. So directly when producing this output stream, you could piggyback your sort-based grouping algorithm. That's one way of doing that, and that's called late grouping. But yeah, that's basically what you see here. Yeah? So you see here, I have these, there's always two tuples, it's only one attribute, here 1, 1. Yeah, with a count star grouping, it leads to 1, 2. This should actually be 2, 1, I don't know why. Yeah? And then the 3 appears twice, 3, 2, 4 appears 3 times, 4, 3, and so forth and so forth. That's this formatting error. If the font is too big, it spills over, I guess, whatever, to fix that. Yeah, so that's basically the expected output. But you could do that earlier. Yeah? So while doing the final merge of external sorting, you could already do that. So for instance, you could say, rather than producing the output, yeah, that's basically what you see here. You first produce the sorted output, and then you produce the grouping result. You could already integrate that into the final merge. So while merging these two sorted input streams, you could combine that with a group by algorithm to never produce the final sorted output stream of tuples, but directly produce a group by result. So you fuse functionality from two different algorithms into the same algorithm. And you can push that down even further. You could say, okay, if you do something like that, you could also do that earlier when creating these runs. Yeah? So when you have these input runs here, and you run the merge operation to merge 4 input runs into a final output run. We talked about that at length. There's no need to maintain the data format if you know the entire purpose why you are sorting is to do a group by anyway. So why not do it earlier? Why not directly group here and count the number of occurrences here in the streams? Yeah? So you could directly go from a representation where you keep the tuples like that to, for instance, replace this 4, with a 4.2. That's basically what I'm saying here, doing here. Yeah? So you see here's a mixed representation. There's some individual values here. There's 2 and 3. And for 4, I have a run length encoded version, 4, 6, 7, 8, 9, and so forth. And I also do it here. Yeah? Now you see, okay, 1 occurs twice in that input here, so I have this run length encoded version here. The 4 appears only once, and so forth and so forth. And that's called early grouping and aggregation. So what are the pros and cons of this? What do I gain if I do that, and what do I lose? Yeah? I save some memory. Memory in what sense? Main memory or external memory or? We save main memory, we save external memory. What else do we save? What does the merge operation do? Yeah, these 4 orange input runs are written out to external storage. Yeah? We save bandwidth, we save I/O operations, we save time, we have less I/O because we have a compressed run length encoded representation that we write on disk. That may be a huge game changer depending on how much you can compress this stuff, but for this count star situation, or if it were a sum aggregate or something like that, oh, that's a big thing. Yeah? So if you keep the 1 terabyte of data, sort it first and then aggregate, versus while sorting the terabyte, or you compress like crazy into this run length encoded representation, that's a huge thing. Yeah, that's a huge thing. Changes. Yeah? Correct. And the same holds then also for reading. Yeah? You read less data, of course, yeah? for every merge operation. That's true. Those are pros. That's a big advantage. So the likelihood is high that the entire thing runs much faster. What is the flip side of the coin? Any idea? What's the drawback? There's no free lunch here. Yeah?
The compression isn't effective, so we have to do all these processes by compressing, but don't gain any main memory.
Yeah, right. Same problem as with all compression methods. Yeah. Could be that the compression method doesn't actually compress. So we do a lot of effort and don't gain anything. Yes?
Well, when we are sorting the normal way, we are just reading from the hard disk, sort them and put them in the hard disk. But here we need to copy.
No, it's the same thing. It's just the data format I'm reading and writing from and to hard disk is changed. Yeah? So here the runs that are merged. Yeah? So here the runs still are the original data. But then what I'm writing, so I'm merging that. In memory, I still have the merged information, but directly in memory, when I have sequences of numbers that are the same, I compress them, and the compressed stuff is written out to disk directly after the merge. So I save write operations, write I/O here. Yeah, one problem is this is an additional effort implementing that. So it's if you just have sort, merge, join, and sort-based grouping, those are 2 operations or operators in the system. You can directly put them into each other, and they will work with little effort. It's going to work. So pushing down functionality deeper into the sorting is typically much more software engineering effort. Another second problem is this only works for certain aggregation functions. Yeah? Here it's counting. It's a so-called distributive aggregation function, meaning you can split the aggregation function into sub-processes. It's basically like a big aggregation tree. Yeah. So if you have whatever your input tuples here, those are my input tuples. What I'm doing is I do an aggregation here, and I do an aggregation here. Yeah. And then I aggregate the aggregates. You see the example here, there's this 4.2, 4 appearing tries on the left side, and then there's this single 4, and they will be combined to this 4 3 times. That's okay for count star, for sum. For average already doesn't work, but you can then compute average as a combination of sum and count star. But if your aggregation function is a black box, so if you have no idea how the plus is implemented, you probably can't do that. Yeah, then you really have to collect the individual tuples once and for all, and then you pipe them into the aggregation function. So it's again a similar situation to as we have with the joins. So there are these join algorithms that work for certain join predicates, and then you can do fancy stuff, but they don't work for all join predicates. The same here, not for all aggregation functions, but for the most important ones, still this works. Yeah, I think it's a very nice algorithm and nice trick know about. Here's another extreme example where I do a count star. That really pays off, but I actually wouldn't do. So your database system shouldn't. I mean, it still looks a bit like external merge sort, but basically it's just counting. Yeah, and on a high level, it's still early aggregation, yeah? Meaning you just count the stuff. But then if you just count, why do you sort? Why do you create sorted runs in the first place? Yeah, but that's an extreme example. Okay, so we learned about these 4 principal paradigms of join algorithms: nested loop, index nested loop. In a special case is a simple hash join. Again, recall, it's just about when is the index being created? Did it exist before? Do I do it when calling the join algorithm? And what type of index is created? For if you do it at runtime, it's typically a hash join. Then this sort merge join and the partition-based, which we not covered today, is not fully correct. We covered it with co-grouping. Basically, what I showed there is a variant of a partition-based index. Gray's hash join is co-partitioning. Yeah, and you can, once you understand these algorithms, you can implement all of these operators. That's the cool thing. External sorting and external partitioning, yeah, those are the key algorithms to master data bigger than main memory. So if you still hear people talking about big data and Hadoop and Spark and whatnot, at the end of the day, it's the techniques I explained today. Sorry, it's the same techniques, often hidden under some weird terminology, but it all boils down to these kind of techniques: sorting, external sorting, to do some sort of grouping, co-grouping based on co-partitioning, stuff like that. That it always leads to these things. So. And there are opportunities to fuse algorithms, like sorting and grouping. That's not the first thing you can do, but if you have a really expensive special case you execute often, you may want to think about it. Yeah, that's it for today. See you on Friday.